Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so my name is Michael Schmidt, and I work with Hal Lipson at Cornell University. And what I'm going to be talking about today is a very specific topic, I guess. This would be majority of my PhD work at Cornell, and some of my more recent results, and all about extracting natural laws from data. So when you guys think of the word natural laws, what do you think of? Anyone have an idea what a natural law is? Can anyone think of one? Do you know a natural law? What? Yeah, of course. Yes, exactly. So that's a natural law. A fundamental law that we can write down in an equation that holds true over a number of systems. So a lot of my interest is if we have lots and lots of data, are we able to grind out some of these nonlinear mathematical relationships and data mine some of these symbolic relationships that are difficult to find by hand. It's very difficult to find some of these by hand. So I'd like to start off with some quizzes for you guys. So here's some data plotted. It's y versus x, and it's got this kind of U-shaped here. So if we were to find an equation that relates y to x, what do you think the equation would be? Do you have an idea what this equation is?
Y equals x squared.
Exactly. So you guys are good. You're off to a good start here. So here's one a little bit harder. Not too much harder, though. So this one actually, I'll give you a hint. No, this one has a cosine in it. Anyone have a guess what this one might be? Sometimes I'll...
Cosine x over x.
Really, really, really close. Yes, yeah, you got it. X cosine x. So here's the one that's a little bit harder. Think about this one for a while. This one's significantly more difficult than the other ones. Does anyone have any ideas? Sometimes I'll give this talk to math groups, and they'll get these like this. And I'll really have to really ramp up the difficulty of these questions.
It's the same kind of data that then you shifted it up by something, so it's repeating, but once in a while it goes up. Not really.
Yeah, in a way, yes. So, oh, what kind of function? Yeah, so this is actually a sigmoid, and it's so you can see the sigmoid is right over here. So it's basically just an S-shaped curve, and it's modulated by this cosine, right? So this is a problem that you guys are actually surprised pretty good at getting these, right? Like you knew the basic building blocks, what was going on, but this is something that we can do with an algorithm, like that, instantly. But you can imagine making this problem much more hard. Say if it wasn't just x, say it was 20 inputs, and we wanted to predict an output. What's the equation that predicts that one? So that's much, much more difficult. We can scale this problem up to arbitrary difficulty where it really pushes the limits of what the human mind can actually understand and do. So has anyone heard of symbolic regression before, this term, symbolic regression? A couple of people are nodding their heads. So symbolic regression is basically you're finding a model, but you don't know what the model is ahead of time. You have to find the structure, the morphology of the model, and you have to optimize the coefficients. So normally in this type of modeling work, you'll start off with a known model for a biological system, and you'll search over the parameters to find the best model. So in this case, we have to do everything from scratch, just like Einstein did to come up with E equals mc squared or something like this. So we represent equations are what we're looking for in our model. That's how we encode a model. It's an arbitrary mathematical model. We can represent these as a binary tree in computer memory. Right? So this is the type of structure that we'll manipulate to fit some data. So our goal is to find the expression, the minimalist expression that explains this data. And as we add different components, we can evaluate this model and see how well it fits the data, how well it agrees with the data, how well it disagrees, until we converge on something that fits it quite well. So our idea is to optimize this model, make it as simple as possible, but also explain the data as accurately as possible and predict into cross-validated data. So that's symbolic regression. And typically this is done with a genetic program. Is anyone familiar with genetic programming? So a lot of machine learning people will know what genetic programming is. So this is an ideal application for a cloud because it's massively parallel algorithm where you start off with a population of, in our case, equations here. And we insert these into a cloud. We run this genetic algorithm. We'll introduce mutation, crossover. We'll vary and randomize these expressions. And we compete them to fit the data. So that's some sort of fitting heuristic. And we'll take the ones that are better than the other ones. We'll throw away the bad ones. We'll keep the good ones. And we end up with, hopefully, better equations. And we repeat this. And literally, we're going to repeat this billions and billions of times. So we're going to search over most likely trillions of expressions and trillions of sets of parameters. And we're really going to exhaustively search the space of symbolic expressions to find data. So ideally, what we want to do is exhaust the search space. This is kind of a representation of equation space, where we have the simplest equations over here, but the most accurate equations are very, very complex. So we want to find the ones that are simple and also the most accurate. And this is kind of what this Pareto front looks like, this front of the model. So this one up here is perfectly accurate, but it's extremely complex. It's not very parsimonious. Or this one down here, maybe it's just one term. It's very, very simple, but it's not very, very accurate. So we want to exhaustively build this front so we can look at this front and analyze what are the best models to explain the data we have, basically. So that's our task in symbolic regression. So I'm going to do something I have not done before in a talk and give a live demo. So hopefully this worked out before. I've never shown you this to anyone before. So this is some software we've developed. You could actually download it online if you're interested to talk to me afterward. But this is basically a symbolic regression application we put together. It kind of looks like an Excel sheet here where we have our data. And here's just some preloaded data I have. And I'm just going to run this on this computer, so it's a little bit slow. You can see what's going on. So hit start here. Okay, so on the right here, we can see this is the data we're trying to fit, and the different colors are just if it's in the training set or in the validation set. And the magenta curve here is our best solution we've found over this search so far. So on the left here, we have all the equations that are on this Pareto front that I just mentioned. So the simplest equation we found that's very accurate, is this single parameter model, all the way up to this kind of more complex model up here, right? So if we give this guy a few more minutes, hopefully a few more seconds, we should see it converge onto the exact solution. So does anyone know what this equation is? What's the equation that generates this one? It's not too bad. Anyone have any ideas? This one's really close. It's kind of bad down here, though. Right? So it's slow on this laptop because I'm running the battery. But we should converge onto something quick here. All right, this is getting a little bit closer. Okay, so now it's fit the general shape of the data, right? So now we can look at these. Whoops, sorry. So here we have the best equation here. This is actually this is the right answer. And there's some noise in this data. So these are very, very similar, but this one has an extra parameter that's overfitting. So the solution here is actually sine of 2x minus x of sine of 2x, and that's what generates this data. And we can see that this is the simplest model that actually explains this data pretty well, or at least qualitatively well for what we're interested in the range of data we have. So that worked. I'm so happy.
So you have three possible solutions, and you're going to go with the most parsimonious.
So I don't want to say ahead of time what you would actually. It's hard to say with a general rule. You'd want to look at each one of these because each one of these is actually an interesting result, right? So this is the simplest equation that's less than 4 terms in this binary tree that fits the data the best, right? So you might be interested in different approximations. So you, as a scientist, you'd want to look through this and see, maybe you'd want to test afterward. Is this parameter real or not, and things like that. And
I was going to ask. So when you do the simulation, do you have a rule for the approximation, the output?
So here we're just trying to find the simplest. For every size of equation, we measure the complexity of equation of literally of how much space of paper does it take to write down this equation, right? So we want the shortest equation that fits the data the best. And we want to find the best equation for all these smallest complexity of equations. So that's symbolic regression. Right. So we start with random symbols, and so we have a certain number of building blocks. We have multiply, addition, subtract, divide, cosine, sine. We have some sort of base level alphabet to build up these equations.
Including things like Bessel functions.
You could do that. You could do that. If you have some prior knowledge, that'd be a great way to say, I know this problem will probably use these type of building blocks, so I'll include these in the search. And it will make it easier on you.
When you're doing the genetic algorithms, because of functional form that might be promising or might not, what's the trade-off between continuing doing GA from a random search versus doing some non-integrating into your other optimization? See how far that doing functional form gets you.
This is a really, I mean, this is a great idea. That's what you want to do. You want to have, you want to balance your search over the morphology and the parameters themselves, right? So there's a lot of research going on now. What's the best way to pick this sort of balance? And you don't want to converge too early, or your whole population goes on the same model and you have very, very little diversity in your search. But you don't want to do it too slow, because then it takes forever to get these results, and you may not find the optimal ones unless you take the time to really search through the parameters also. So in this case, we're just using the mean absolute value to fit this data, and we're just randomly perturbing these equations. So I'm going to move on. If hopefully I do get to what you're interested in, and if I don't, stop me. I'll go over it more. What am I starting here? Okay, so that worked out well. So there's a number of ways you can apply this. I mean, some of the areas I've applied it are in metabolic modeling. So this is the largest system that's ever been identified automatically with the computer without using any prior knowledge about the metabolism of these cells and things like this. So this is a 7-dimensional ordinary differential equation system. This is a nonlinear dynamical system. So we find each one of these equations, and this is almost exactly equal to what is known in the literature for this particular system, with the exception of this term here is approximated. So we're able to reconstruct the general morphology of these systems pretty well. You can go through this and can see that the rate of change in this chemical is exactly proportional to what this equation says. And you can build up kind of the metabolic network from these type of models. Another useful area that we found for symbolic regression is solving some difficult type of math questions. This is a new model a new solution we found to a very, very famous question that colleagues like to ask themselves in the physics community. I don't know if you've ever heard of this before. If you're given f of x equals x squared minus 2, what is the solution? So sometimes it's just passed around among faculty. It's a test of your intelligence. So we're able to use GP to find a whole new solution to this and do it faster than the fastest record time of any physics professor. Oh, well, who cheated, us or the algorithm, right? So we just use technology. And so we can also do other different types of more challenging problems, finding simpler models than what's existing in the literature for a lot of these systems is another area that we're exploring. So everything I've shown you is doing predictive modeling, right? So we're building a model of the system. We want to know what happens next. How does the system evolve over time? How does it change over time? So what I really want to emphasize in this talk is proposing a new way to go about this sort of modeling. So rather than building a predictive model, what I'm proposing is, why don't we look for, instead of looking for what does change and how does it change, why don't we look for something that's invariant? What doesn't change in the system? And what won't change? What won't happen as the system evolves? It's kind of an opposite way of looking at this type of modeling approach. So why would you ever want to do that? So here's a picture of a pendulum. It's just a washer on a string, and it's kind of swinging back. And we might want to say, we could predict where this pendulum is going to move, how fast it's going to move, and things like this. But there's things about this pendulum that don't move. Can anyone, or that don't change over time? Does anyone know of something about this system that doesn't change over time? Right, exactly. The Hamiltonian of the system, the total energy. That does not change at all. So that's something that's not true just for the pendulum. It's true for many, many systems, right? And although we can use the Hamiltonian to predict the dynamics, it tells us something deeper about this type of system. It's conservative, right? Energy is conserved in the system. So in some sense, this gives us deeper insight than just predicting where the pendulum is going to go. It tells us something that tends to hold true not just for pendulums but other things. For example, a helicopter engine, right? So something like conservation of energy also applies to a much more complex system like this. But this poses a challenge, right? So a conserved or an invariant equation is just constant over time. So can anyone tell me, say this line is your data. What's an f of x? What that corresponds to this type of data? Does anyone think of one? Usually people will shout f equals 42 or something like that, right? So that's an equation that's conserved for every system, right? It's trivial in a way. So finding something that doesn't change is super, super easy, right? Just f equals 42. So, but how do you find something that's not trivial, right? So something that relates to system variables but also doesn't change. So this would be a non-trivial f of x, right? So it turns out there is a way to do this, and we found a way to do this, and we only got a really cool publication out of this in Science, but how to search for and find these invariant expressions automatically. And I'll get into how we do that in just a second. So this is our key figure in the paper. We took this nonlinear double pendulum. We get this sort of data, and we feed this to a cluster of computers. They grind away in this GA, and they spit out, hey, this is the expression that doesn't change over time, right? Tells you something deep about this double pendulum. So if we go back here, we can't just fit data to anything because we don't have a signal. We're looking for an equation that doesn't change. So the insight here is we want to look at the implicit derivatives of our data. So an implicit derivative, I don't know how long it's been since most of us have taken calculus, but if you take the ratio of partial derivatives, you can derive these implicit derivatives, like this delta x over delta y, directly from the data. So we have if we have a candidate equation like the total energy of an equation, we can derive the same relationship by taking the implicit derivative. And see, the f signal here cancels out. And we're using the f to derive the same partial derivative from a candidate equation as we have in the data. So now we have a way of matching up an equation with the data and justifying a model from the data, even for these invariant expressions. So the algorithm that goes through this, we start off by pre-computing these partial derivatives. We collect data, we pre-compute the partial derivatives. And then we go into the search phase, and this is something you would offset into a cloud somewhere. And we're comparing, this is the GA, we're comparing our population of models. We're measuring our fitness, we perturb them, and we kind of grind away at this as long as it takes to get some interesting results. And then we spit out what are the most parsimonious results that are invariant, the most invariant, but also the most parsimonious for your data. So here's the system we use for in the science paper. We have this motion tracking camera, and there's me holding this double pendulum here. And we have basically, the system uses these cameras. It has these kind of infrared markers on this pendulum. I don't know if you can see them here. But it can track these over time at about 1,000 frames a second. So really we have a system that can kind of look at some interesting phenomena in nature. It can actually look at it itself and automatically spit out the equation for it. So this is really a digital physicist, or at least as smart as like a freshman physics student in college or something like that, right? We have a computer that can do this. It can look at it and figure out what are the dynamics or what are the equations that could actually correspond to this. So this thing's kind of fun to play with, and I'll give you an idea of how it reacts. A lot of people are surprised at how complex this system is just for being a simple two-component device. And the reason why we chose this system is this is a system that you can't predict. It's chaotic. So this is the thing about chaos. It's very, very sensitive to all initial conditions, and your error increases exponentially as you try to predict this system. But you can model invariants of this system very, very accurately, even though it's chaotic. So even though this thing is moving crazily, you'd have a really hard time building a predictive model. But we're going to show that we can find an invariant model of the system much, much more easily. So this is the data that we get out of that motion tracking for the double pendulum. So if you're the algorithm, this is what you see, right? And you're going to say, all right, I have all these variables over time. How do I recombine these into something that doesn't change and isn't trivial? So this is the problem we're posing to the algorithm. So we're going to use the GA, just like I showed you before in the demo. And here's a visualization of the search. And this is going to show the best equation that's been found for the system over time. And you can see these sort of evolve. The equations are represented as an acyclical graph, or you can interpret this as a binary parse tree. And the algorithm is evolving these solutions. You can see different components, subtrees are evolving independently. You'll see some recombination where this part is conserved, only this part is changing. This is kind of an interesting way of looking at how this GA actually operates on these expressions that are represented as parse trees like this. And eventually, this converges down onto the exact solution for the Hamiltonian, the total energy of the double pendulum. And that search, the video took about 30 seconds. So this search for us took about 40 hours on about a dozen or so servers, quad-core servers. So this is a very data-intensive search. So another way to visualize this is, I showed you earlier, we're interested in the Pareto front, the parsimony of the equation and how accurate it is. So we can actually see how the equation searches over this space of equations also. And you can see, this takes about 5 minutes so you can see it. It's actually searching down here. It's off the graph. All the interesting stuff happens up here. Is it tends to find the simplest equations down here that are very, very simple and inaccurate. And it tends to build up kind of bloated solutions that kind of recoil back towards simpler, more parsimonious solutions. So this is kind of interesting if you're interested in genetic algorithms or genetic programming to see how the solution actually comes about. It's not a direct route to this, but it has to take this very indirect route through the genome of what you would consider an equation to get it to the exact model. And this is the exact Hamiltonian up here at this cliff up here. So this is the front of solutions we get over time for the double pendulum. And here, the intensity here, the darkness, is how much time did the algorithm spend here. So we spend a lot of time on these kind of intermediate complexity solutions until we finally get up to the exact solutions up here, and then we kind of grind away at the more accurate results up here. So on this front, it's actually kind of interesting. Here are all the equations. First of all, does anyone know what the total energy for the double pendulum is? This is actually kind of a complex question, a complex solution. So we can look up here. This is the exact energy conservation for the double pendulum. So what's interesting about all the equations on this front is they're all different approximations of this Hamiltonian equation, with the exception of this one, which is another approximately conserved result, which is the conservation of momentum of this double pendulum. So this only holds true at really high velocities where gravity is negligible in this case. Then this becomes actually approximately true. So we also find that there's also these approximate conservations that lie on this Pareto front, which is a very interesting result in itself.
Where's angular momentum?
Oh, omega here is angular.
No. I'm sorry, conservation of angular momentum. That's also,
Yeah. That's what I meant by conservation of momentum, the angular momentum. Because we're only looking at the angles on this system, the two angles here. So we did this with a number of systems, and when you search for these using the implicit derivatives, you get lots of different results. You don't necessarily always get the Hamiltonian. You get other things that are conserved. You might get Lagrangian equations. The sum of forces is constant over time. If you look at just a single pendulum, you look at the XY values, you find that the radius of that circle of the pendulum is conserved. Things like this. So I'm going to speed up here to finish so I have time for questions. So we did some other systems, 4D systems, a chaotic spring pendulum system. This one's very difficult to visualize because it's in 4D, so I'm sweeping one of the variables here. But this is the results you get. You can model these surfaces and not just predict single values and trajectories. You can predict entire surfaces of solution spaces and things. And finally, if we repeated this experiment with lots of different sizes of double pendulums, different masses, different lengths. We also showed in the paper that we could find the equation for the bulk parameters in this model, the K2s, the K1s, to relate them to actual physical constants and things like this. So in the end results, we can get the full, you might think you pulled this right out of a physics textbook or something like that. We can get the full equation that relates all these physical parameters of the model with the Hamiltonian itself. Also, if we do this with multiple systems, we can pull out common terms and build up kind of an alphabet of physics. A library that we can pull out to model all these type of systems, like the angular kinetic energy, the linear kinetic energy, the potential of a spring, the potential of a pendulum, and things like this. And we do this by looking at the frequencies of different terms we find in all the solutions. And we found that terms that tend to be complex and also frequent in these solutions tend to be the most physically meaningful. So this is another Pareto space of just the terms and how frequently they appear and how complex they are. So this is a way of gleaning off the building blocks for these type of systems and doing future modeling on related systems. So just to conclude, I have 2 points to make. Is that you can use the cloud to extract these sort of nonlinear mathematical relations from your data. And invariant models are a useful way to give you deeper insight into these systems than purely a predictive model. But the caveat is actually more challenging to search. So thank you very much.
Questions?
What do you, how do you see these laws, when you derive a certain equation for something, how do you see it being able to expand beyond the domain in which you're testing it? Like, sort of how much do you trust it beyond, like, just the double pendulum that you have installed on that table?
So we can always, well, the one way to do it ultimately would be to take another double pendulum, refit the parameters, and see if it makes the accurate prediction. See if it predicts that the energy is conserved. If we see the energy increasing, we might get suspicious here. Right? So the best way to do it is with cross-validation. And ultimately, these are white box models. So we can look at them and interpret them and see if they actually make sense. They're amenable to human interpretation. Even though sometimes looking at equations can be confusing. But for an expert, they can look at these sort of equations and see, yes, this is exactly what I'd expect for a potential energy term and things like this. So there's ways of doing it intelligently through expert interrogation of the model, and also using cross-validation, looking at other systems that weren't used to find the model, and things like that.
So how much would you trust it if this was not a physical system where you can do the experiment? You're just given a whole mess of data, maybe complex ecological systems.
This is,
where you have no
yeah.
idea of anything, and you come up with something. Would you engage in something like that?
This is exactly what I'm interested in, right? So this double pendulum, you can look at, you can see it's got these arms, it's got these two angles. Take a biological system, you can't look at these reactions and seeing what's pushing on what and what's being conserved exactly. So this is the area I'd like to take this. And the only way to do that is with testing the predictions. You find the best model and you test the predictions. Richard Feynman's famous for saying this is what you do in physics, right? You guess the model and you test the predictions. This is a way of doing it more with a more data-driven approach. So there's a potential there to do this more quickly and accelerate our ability to look at the more interesting questions, or lead us in the interesting directions for that type of system. But ultimately, yeah, we have to test predictions, and then we might start to trust it and publish it and whatnot.
But then on the other hand, if you're confident enough, you can rewrite Physics 101 lab.
True.
Right? It's
Well-
interesting when it's
Yeah.
outside of physics.
Right. Well, Physics 101, especially for other discipline students come in, they measure data right on their notepad, on their notebooks.
Yeah.
And then they kind of like predict and then the natural law. But then this is another way to show them. So they can just move the pendulum, let it go, and then see how the computer produces the natural law.
Right. So that would be interesting because you could say this is a completely different way of how a human would go about solving this problem.
But the double pendulum is already probably in the last chapter of Physics 101. So have you done anything simpler?
Simpler.
Just to model a...
So single pendulums, of course.
Yeah.
The interesting result we have now is we do have some biological results where we found conservations, and we don't know exactly what they mean yet. So we have these conservations for some gene regulatory circuits that we're looking at. And they're perfectly conserved. They predict the dynamics beautifully, all the implicit derivatives. And right now we're in the process of sitting down with the biologists and saying, okay, we need to interpret this because we can't just publish an equation. We have to say, here's the answer, but also here's how you justify and interpret this answer. So really we're coming to this point now where the computing can give us the answer, and the major challenge we have is interpreting that answer. So this is the kind of the next frontier, I would guess. I don't know if I'll tackle it in my work, my PhD yet, but I think in the next few years, that's going to be a major problem, is interpreting the answers that we're able to glean automatically. As these number of answers we can get become better and better and more useful and useful.
Very interesting. Thank you. Also, since you are last speaker, take your own time.
I'll take my own time. A quick question observation, Pendulum, what Sergio suggested. So it strikes me that you have a really complex set of data that comes in from biology or environment or something.
Mm-hmm.
Now, your pendulum, you can identify what your degrees of freedom are. These angulars or these momentum.
Mm-hmm.
But I would think you would also want to be able to, if you could deduce what the actual degrees of freedom might be. So various of your measurements might actually be correlated.
Yeah.
And perhaps we have.
So there's this problem of feature selection, right? What to actually...
Well, feature selection and maybe be able to reduce the number of degrees of freedom.
Ah.
So
Do you think you do that with an optimization? Because that's another deep question, right? Is what to constrain to help your search, right?
yeah, because in this case, the degrees of freedom is, going into anything, the data are the degrees of freedom. And maybe those are not the best degrees of freedom for the next situation.
Yeah, you're right. That's an interesting point.
This part, yeah.
Very interesting. Thank you for your
Thank you
feedback.
again, Michael.